I'm sorry for the delay, and which happened under circumstances that didn't depend on me. So my name is Stephan Rudykh, and I will be talking about two topics. The analysis that we use are quite similar. These two topics are elastic waves and instabilities in hyperelastic fiber composites. So there are two names also appearing here, Slava Slisarenko and Pavel Galich. They work with me, and they contributed a lot to this work. So so I'll start from talking about waves, and this is something that I typically show, but indeed in this forum I don't need probably this cartoon. So indeed, how waves propagate in the material depends on the material properties, and we also can think about the microstructured materials. It's just a schematic of a laminate, and then the elastic waves propagation will depend on the microstructure. And we indeed can use the geometry and material properties and design situation when the wave will not propagate. We'll call this band gaps, and it's one of the aspects that we'll be after. So I will start from simple materials, from homogeneous materials. The only thing that we do here is it's a little bit different from a typical analysis. So first we deform the material, so our materials are very deformable, and then we do the standard small amplitude motion analysis superimposed on these large deformations. And then you have this standard mapping of the deformed and undeformed configuration, and then again your small amplitude motions are superimposed on the large deformations that we somehow induced in these materials. Again, reference and deformed configurations. Just to write some simple equations, so we have these equations that can be written in the undeformed and deformed state, and all the stresses and other.
Why Cauchy is true?
Well, that's.
I start quarreling with you. Call it Cauchy stress. Stress is Piola stress.
Yes, we have Piola too. Probably that will satisfy you. So I explained why I put it through here.
Told you what is true?
Sorry. Just change it to false.
Okay, false stress. But so I just use it typically when I explain it to students, and then when they measure, sort of do the uniaxial tension, then they measure forces.
Participate in spreading this false idea about
well, I started from apologizing for, probably it wasn't enough. Okay, so with this spirit, we'll continue. This is something standard, except the use of the word true. Okay, Piola. Actually, I corrected it on the plane, so there was a definition through nominal stress, but anyway. So then we do the small amplitude motions here, so superimposed on the quasi-statically applied large deformation. So here everything is linear. You will see the linearization of the Piola, and indeed it's not increment in first Piola-Kirchhoff, just Piola. And then for homogeneous materials, we have this ansatz of plane waves. So we just don't have any microstructure here. And then it's a very standard thing that leads to the eigenvalue problem. So we just need to identify our acoustic tensor Q, which is related to the tensor of elastic moduli to the material properties. And so now I'm just specifying two energy functions, material behavior. Basically, it's one model, just one is a part of the Athanasius and Gent and Neuken model. So for Gent, we have also the shear modulus, and we have also this what is called locking parameter, and when this locking parameter goes to infinity, then we reduce to very simple but nonlinear Neuken model. And the difference between them, just to illustrate it here, so this stress stretch curves. This one is for the Neuken model, still nonlinear, but without very pronounced stiffening. But once we increase the locking parameter, we can observe and obtain these stiffening effects. Right, so that's just to illustrate the difference between these two models, and then you just can take this. You add some compressible part to the model, and then you allow the pressure wave or longitudinal waves to propagate. Or again, you can reduce to the EUROMECH model that we just talked about, and then straightforward. What you obtain is just you take a second derivative with respect to deformation gradient. You obtain your acoustic tensor. For gent and for EUROMECH materials. So this was something it's quite well known. I just would emphasize here is how deformation affect the wave propagation, and even in this homogeneous and very simple material. So this I plot the velocity, the phase velocity, as a function of the direction of propagation in the undeformed material. And then once you apply deformations, different stretches, you can observe that you have very different. You can actually slow or increase your elastic waves propagating in the material. Again, you can apply tension or compression, and that will change. You can actually speed up your velocity. Okay, so another interesting feature here is that when you apply some large deformation, shear wave, simple shear type of deformation, then what you can do, you can actually split the pressure and shear waves. They typically, they indeed go in the same direction, but in this case, pressure wave will not really care about the deformation, but shear waves will be inclined. And you can do this also with another type of material that I will not talk in this presentation of the electric elastomer. So you can electroactive materials, so you can use electric field to achieve similar effects. Again, there is nothing really fancy here. Just my materials are really just homogeneous materials. So I'm going now to a little bit more complicated. So we'll introduce a microstructure, and so now start talking about the layered materials. Also, a rather simple material that allows treatment of the analytical treatment of this problem. So again, we're after here the situation when we can create band gaps, cancel some particle frequencies. That's what we will look into. So this is a dispersion curve and waves go in the direction of layers. Typical dispersion curve with then deformed laminates. Now I start deforming these materials, and what I want to do here is that I compress the laminates, and at some point, so we have, again, I probably should explain it in more detail. So we have soft matrix and stiff layers, and when we compress in direction of layers, then these stiff layers will buckle in some type of a wavy pattern, and then that affects the wave propagation in the same direction. In that way, that we obtain a band gap in situations when we didn't observe anything in the undeformed state. And then we can continue deforming the material and obtain these band gaps. So you can obtain it for different this phenomenon of inducing band gaps by deformation and instabilities in polymer composites with similar or identical densities, and you can obtain similar behavior also from for different stiffness ratio and different wavelengths that you induce by your instability. So what happens here, it's, in a way it's quite simple, but maybe we'll provide with a little bit more detail. So what you see, so first that you change the geometry, but the change in the geometry is not really very significant, so there is some deviation from this flat layers. But also what you induce here, and I plot in colors the homogeneous distribution of the deformation. And again, going back to the to the example of wave propagation homogeneous material, so we see that basically in this different region the wave would fill a different material. So you create in a way more complicated composite material. Is also the material to begin with was very simple, just a laminate, and then in that combination of the geometry change and the change of the local properties of the material, that would give rise to these band gaps in this situation. So so we can go a little bit look into a little bit more in details of the change of these two parameters of the geometry and the change in the material properties of the phases, and to just ignore the buckling phenomenon. For that, I will just apply tension instead of compression, and then everything becomes relatively simple, as indeed we know how the thicknesses will change as we apply tension, and and we also can obtain the estimates, the exact solution for this problem for large deformations, and we know how the properties of each phase of the matrix and the stiffer layers will change, and so I don't need a reinstall disk, not now. Oh, I actually said that I do need. That's probably okay. So I don't know how. Can I stop it? I'm sorry.
There is the bomb exploding.
Can I just? Oh, wow! Oh no! Please don't.
I think that you had troubles for what happened in St. Petersburg. Airplanes were bombed.
I don't know what happened, but there were many planes that were delayed without any reason, just for hours. Yes. So back to laminates. So for finely deformed laminates, we can obtain exact solution for in frame of large deformations, and then from this exact solution we can construct an effective energy function, which is here. And again, once we have an effective energy function, it's straightforward that we can derive acoustic tensor and the velocities of the wave. So in that way we obtain the long wave estimate for elastic waves, for shear waves here. And everything here is expressed indeed in terms of the micromechanical parameters. So we use just the properties of the phases and the volume fraction, the concentration of this. So no fitting, just give us what the information, what the materials are in the composite, and that's the estimate in long waves. Another good thing is that there is an exact solution for that, but only for one case. Basically, otherwise you need to use some transfer matrix method. But if you send the wave propagating perpendicular to the layers, and there is a well-known exact solution for that, which gives you the dispersion relation between the frequencies and the wave number. So the only thing that we can update it here, we need to account for large deformations. Then again, we know how the properties of each phase will change with deformation, with the stretch. We also can calculate the change in the geometry, and if the material is compressible, some sort of bizarre exotic material, then we can also account for the change of the density because of the deformation. So now we can put this into comparison for the Neo-Uken material, and you see that there probably cannot really see it very clearly here. Indeed, it's because of my computer. So you have the long wave estimate, but it works actually surprisingly very well with a very wide range of the wave numbers. And here the exact solution is for shear waves, also for gent material. The material is already quite deformed quite significantly, and also for pressure wave we have these estimates, and you can observe that the difference between these curves is not really very significant. It's significant in the interesting region, actually right here, where all the band gaps form and burn. So that's the long wave estimate cannot really provide us this important information. So, and again, that's where the band gaps appear. So this for shear and pressure wave. This is something quite standard.
Sorry, which is the microstructure beyond or under this band gaps structure?
What it again?
Forgetting these band gaps, you have a microstructure in your laminate.
Oh yes, so that's why you have these band gaps.
Yes. So how do you get this? Which is the microstructure which is causing it? Changing which parameters can you do this bigger or smaller?
So yeah, I will actually. I'm going to show that what happens. So okay. So I'll need 2 more slides for that. So first, I just want to illustrate how the these band gaps change with the different parameters, say volume fraction, different stiffnesses. For example, by knowing this and analyzing this, you can easily design a material with very wide band gap, just with the right amount of soft or stiff material. And then, so again, I'm getting probably to the answer to the question. What happens here is that so this for undeformed, so we have pressure and shear band gaps together, and so the dark areas with what I would call complete band gaps, when you don't allow propagation of the shear and pressure band longitudinal waves. And what happens is, so when I apply deformation, it's 50% of deformation. So you can observe that shear wave band gaps, they don't really care about the deformation. There is a reason for that. Next slide. And, but pressure band gaps, they do change a lot with the deformation. And so this slide I just want to show that this for in-plane deformation, when we don't allow deformation in the third direction. And I want to show it just it's something that is not really related to the type of deformations that we apply in 2D and 3D. There is no limitation for that. So indeed, gent material will produce changes in the shear wave band gaps, but for now, and this is equibiaxial, so 3D type of deformation, and you also can see that shear band gaps, they stay the same, but pressure band gaps change a lot. In gent material, you also see that shear band gaps change, and I'm going to explain it a little bit in more details. So what happened is that the pressure band gaps, they change mostly because of the change in the geometry. You just change the thickness of your layers as you pull, and pressure waves, they typically will not care about the changes in the material unless you really have a very compressible sort of auxetic materials. Then you can also affect the pressure waves through the change in the material properties. So for shear band gaps, there's actually a competition of the geometry change and the material property change, and it magically appears that for Nyalukian material, these effects, they completely cancel each other, so they just there's no change because of that. But if you choose a different model, gent or Ruda Boyce or whatever you would like for your materials that provide some stiffening, then you can overcome this balance between the material properties and the geometry changes with the deformation. So, well, this is just to remind that with different volume fractions and material properties, we can tailor these band gaps and cancel frequencies at different ranges, and we also can use instabilities to achieve even more tunability of the acoustic characteristic here. So we've done also some work on fiber composites in 3D, and basically the procedures that we've done, the analysis is essentially it goes along the lines that we've done also for laminates. So we can, again, construct an effective energy function, and again, everything is in terms of the actual microstructure parameters, volume fractions, and the properties of the fibers and of the matrix. So we, again, don't do any fitting here. Just, and then we have these, again, the same procedure, I derive acoustic tensor and have the long wave estimates for the phase velocities, and that's how the slowness curves would look like. And there are some very simple expressions for the phase velocities in particular cases when they aligned with the fiber direction on perpendicular to that. So, and then to account for the to get information of the wave propagation at the wavelengths comparable with the microstructure, so we do Bloch wave analysis. It's done numerically. You don't have analytical solution for the third direction. So there is an analytical solution if you work in 2D. It's but we wanted to look into something something new. So in the third direction, and then you can see how the comparison between these full Bloch wave dispersion curves and the long wave estimates. And indeed, you expect that the long wave estimate will work very nicely here, but then there is a very pronounced dispersion. Again, it depends on the on how much, what the amount of the fibers that you put and what the contribution of the fibers in terms of stiffness. So with this I end the part of the elastic waves and I go to instabilities. And I don't know how much time do I have.
You have half an hour.
Another half an hour?
No. You are over half an hour.
Okay, so I'll just go very briefly with this. So the instability already showed one of the examples of these laminates when we compress them, and just here going a little bit more in the details. And these pictures, maybe it doesn't look like that, but these are actual experimental.
You have 4 minutes, but we can wait some 10 minutes, okay?
I think I can, okay, thank you. So this is actually experimental picture, also might not really look like that, of a 3D printed layered material. So again, I compress it in the direction of layers and inspect them to buckle. That indeed what happens. And we can print different volume fractions of these phases, and we obtain different wavelengths, and we also can print different materials and go straight to long wave type of instability. So this is just to illustrate that it indeed something that we've done actually experimentally. I can see these wavy patterns form, and it's very actually like it very much because it really agrees very well with analytical predictions, the wavelengths and the critical strain, etc. So the analysis that we very briefly that what we do here, again, it's we use block Flaquet analysis, and we scan for any k to find the right wavelengths for these instabilities, right? So, but you can do sort of analysis that is a little bit simpler. So when you just say I will be after a macroscopic type of instability, so I will be looking for the long wave type of instability, then you can just obtain the effective tensor of elastic model and just do the loss of ellipticity analysis. That is a particular case of the full block Flaquet analysis here of the instabilities. So, and then with that you obtain all this information, then you can give it to the finite elements and help to find the finite elements to find the right mode of buckling, and then you can obtain the what is called post-buckling analysis after, again, stress strain. You can also measure amplitude here. So you continue, you go with this line, and then you have this buckling when you have the softening of the material, and that way where the amplitude of this wavy pattern start growing. What basically happens is, especially when you do experiments, so once you manufacture these materials, you define what is the thickness ratio between the stiff and soft phase, and what are the materials, so the stiffness contrast is also defined, and then you basically essentially end up with one particular unique single wavy pattern that you can turn. And if you're interested in expanding the pool of microstructures that you can obtain with the instabilities, then you can start considering inelastic behavior as, for example, a rate-dependent behavior. That's what we've done. I'm showing here the experimental results for the same identical material, which is loaded different strain rates, and this is something that you wouldn't expect, that if I load it faster, then at some point I will already at the same strain level, I will achieve instabilities, while for very slow loading there is nothing, and we still have a simple type of primary solution for the without any buckling. And then we can also increase further these the deformations, and you'll see the difference between these patterns that we can obtain and at the same identical material just by playing with the strain rate. So that's for laminates. Again, fibers we also have an exact, not exact, closed form estimate for the macroscopic type of instability. It's a very nice formula for the critical stretch. So once you get to you compress you fiber composite to this level of the stretch, then you expect the instability. And then again, everything is here is expressed, all the components are expressed in the actual volume fraction of the phases and the properties of the phases. And probably we'll just it's almost the end. So this is again critical stretch, which is less than 1 we compressed our material, so this curve separates the stable domain and unstable domain. That's where we obtain long wave estimate. And I'm going to compare the 2D layers with 3D fiber composites. Their behavior typically, in fact, the analysis and the solutions for 2D layers were used to estimate the behavior and failure of 3D fiber composites for quite a while. And just showing here, there is some difference between them. So again, I also can do layers in 3D. Not much of a difference. And here's the failure curve for the 3D fiber composite. But again, this is something for only macroscopic mode of instability. Now, if I go to smaller volume fractions, that's where I have these wavy patterns. So here I expect that there will be something. I do microscopic analysis. That's what I obtain for the layers. But if I do this for the fiber composite, so you will see that there is a very significant change in these critical stretches, and there also we'll see there are different patterns that we can obtain. And the patterns are basically defined by the wave number or wavelengths that we obtain, where the instabilities will develop first. Here is the dependence for these layers, or the same layers in 3D deformation. You'll see that the patterns that we obtain, the waviness is more or less the same. There are almost no change. And that is reasonable indeed, because basically we're dealing with the same microstructure. But if we take the fiber composite, the difference between the wavelengths that will happen here can be with the factor of even 8 for particular volume fractions. And you can see as I decrease the volume fractions, how these patterns of the critical wavelengths change, and you actually even can develop this helical type of buckling.
Vibration modes.
No, so it's when I show this, and sometimes people say, "Well, you're showing some higher modes, and the material will never go there." No, this is the actual buckling mode that the material will develop. So that's I would say that's the first mode, if you think. Yeah. I'm just summarizing this, that with the instability we can obtain these switchable wavy microstructures, can even tune them more with introducing in some rate-dependent behavior, and there are quite significant differences if you try to to predict the behavior of 3D fiber composites by the analysis of 2D layers, so you can overestimate some important things. And I don't need another half an hour. And I apologize again.
I have several questions, but first,
you mentioned several times long wave analysis. What do you mean long wave?
Oh, basically, you just take you still have the microstructure, but your analysis doesn't really see the microstructure. You just see the effective properties of the material. That's.
But usually the effect of microstructure is visible only if wavelength is comparable with microstructure characteristic length.
Agree. Completely, yes.
But in long waves, what I would like to understand, what you mean long waves?
But okay, so I think it is actually something very classical. It's not that I'm making up stuff. So again, you have say some composite materials, and for the waves that will be long enough, you will not see the microstructure, right? That's exactly what I'm repeating what you said. But the wave will fail the effective properties because of this reinforcement. So that's what it is. And in terms of instability analysis, so you can predict only long wave failure mode. So we will miss. If there probably will be something, and actually happening something at a very small length scale. But with this analysis, you just cannot really get there because you just take effective properties.
There is something, but you told that in the case long wave approximation, non-elliptic condition is not satisfied. You wrote somewhere.
Right. That's where I actually obtained it.
It means Adamar instability examples.
Absolutely, yes.
Very consistent. This is a bad equation of state. So you cannot use this equation of state because you can calculate.
Well, until this point, everything is fine. You satisfy the mark condition, then you deform it, and then you get to the critical. At that point, I say, we found this. Okay. Yes, you have to stop, and you have to do something else after that. I agree completely.
You said that the last example, when you have 3D fibers,
Okay.
they become the helix.
Uh-huh.
So that means that there is a torsional buckling. I don't know. I can't see where the torsion comes from.
I don't have really the answer for that. It's something that actually, it's quite recent result. I don't know why it happens. So what I see in simulations is that you have two buckling modes and developing perpendicular, more or less close at the same point. And that would lead to this, probably, to this helical structure. But then the thing is also that you, in a way, you induce some directionality, which is not really, somehow breaks the symmetry for some reason. I don't know why. It's just something to look into.
In any case, I would suggest that we talk that you should give a list of parameters, ranges, where you get band gaps, and if you have a total band gap behavior, so that no wave is propagating in that case. Because there are many people talking about these things, but we should meet a precise determination. So we will talk about this, but for next presentation you do. Maybe you should say, look, we are so good that when you choose this microstructure, you get no wave propagation.
At this and at such and such frequency, kilohertz.
Exactly.
Okay. Yes. So, well, indeed,
But anyway, you get a total band gap that for a given for a given range of frequency, no wave is propagating.
Yes, but this is very sensitive to the direction. You really need to go only perpendicular to the layers.
Okay. So a total band gap in one direction.
Right.
Okay. You have to tell everybody this immediately.
But this is not new, really.
Okay, so let's go to a topic. There is topic. There is another question?
Okay, just a question about the situation where you have new current materials. What is the level of deformation that you need to change significantly the band gap? For classical
For neoken material, you actually, again, there are two things. So if we separate shear wave band gaps and longitudinal pressure wave band gap. So for shear wave band gaps, you don't have any change. And that's because you change the geometry, the thickness, and you also change the effective properties of each phase in the same way. But for other material, you can change that. So for pressure wave band gap, you obtain the change because of the geometry. Just it. I can go back to this slide. I just hope I don't take too much time here from others. So.
No.
So you see, so this is undeformed state, and these gray are shear band gaps, and this is the bluish there for pressure, and then when they intersect complete. But let's ignore this. And this is already deformed for 50% of deformation. So for pressure, so for shear wave band gap, it just doesn't matter how much you apply. For pressure band gap, it's just how much you want to change the thickness. This is for neoken. For gent material, that will be different. I'm going back. I know I'm going forward. Here, so you really you need to go to the close to the where the stiffening starts. Start to induce something. This is stretch. So when it's one unit, you don't deform. So two, it's already 100% of deformation.
One and it's become two.
Yes, right.
Okay. Very huge. Okay.
But this is for, you sort of put in an arbitrary number for stiffening, so it starts stiffening. You can put an arbitrary number that will produce a stiffening and 5% of deformation. That depends on what is it realistic for your material that you want to model.
Okay, let's go to a coffee.